In this video, we'll start introducing two important quantities related to vector fields, and these are the curl and the divergence of a vector field. In this video, we'll cover the curl of a vector field, and let me start with the definition. So, if f with components p, q, and r is a vector field, in R3, and the partial derivatives of p, q, and r, which are functions of x, y, and z, they all exist, then the curl of f is the following quantity. It's denoted curl f, and it is itself a vector field with the following components. The first component is dr over dy minus dq over dz. So that's the I component. The second component is dp over dz minus dr over dx. And the third component is dq over dx minus dp over dy. So as I said, these components of our vector field f, p, q, and r, they are functions of x, y, and z. So the curl of f has components formed by taking the various partial derivatives of these functions p, q, and r, and taking this combination of those. So to help remember this complicated looking formula, it is often useful to write, and it's another notation for the curl of f, to write Nabla cross f, where Nabla is thought of as a vector. It is not really a vector because it has as components these partial derivative operators. But if you think of Nabla as being this 3D vector, and you look at the cross product of Nabla and f, remember f is this vector field. Remember that the cross product of two vectors can be computed as a 3×3 determinant. So if you write down that 3×3 determinant, it will have the basis vectors I, j, and k in the first row. The components of the first vector, which is Nabla in this case, in its second row, so that's d over dx, d over dy, and d over dz in the second row. And finally, the third row is filled with the components of the second vector in our cross product, which are these functions p, q, and r. So if you expand this determinant along the first row, you will get exactly this expression. You can go ahead and check that computation. So this is the curl of a vector field. As I said, it itself is a vector field. Let's start with an example. Well, let's consider an example. Take the following vector field f, depending on x, y, and z, with components x, z, x, y, z and minus y squared. So these are our P, Q, and R. And your task is to find the curl of this vector field. So pause the video and use this definition to compute the curl of F. Okay, I hope you paused it. So if you take these components and plug them into that formula, you will obtain for the first component of the curl, you have to take the partial derivative of minus y squared with respect to y, so that's minus 2y, minus the partial derivative of the second component with respect to z, so that's x times y, if you differentiate that with respect to z. So that's the first component of the curl. As for the second component, take the partial derivative of the first component with respect to z to get x, minus the partial derivative of the third component with respect to x, which gives us 0. So that's the second component of our curl. And finally, take the partial derivative of the second component with respect to x, so that's yz, minus the partial derivative of the first component with respect to y, so that's going to give us 0. Okay, so the curl of this vector field is minus y times 2 plus x, x, and y times z. Okay, so with this example done, now you know how to compute the curl if you are given the components of your vector field. Let's look at a theorem which tells us that the curl of a gradient field is always the 0 vector. So our theorem says that the curl of a vector field that was obtained by taking the gradient of some function is always identically 0 everywhere. It's a 0 vector. Okay, so the proof is pretty simple. Okay, so this vector field, this gradient field, Nabla f, has components f sub x, f sub y, and f sub z. So when you compute, so this is the P, Q, and R for this vector field, and when you compute the curl, what you will have in the first component, so the curl of this vector field, we'll have in its first component the partial derivative of fz, f sub z with respect to y. So it will have f sub z differentiated with respect to y. So that's a mixed second order partial derivative, f sub zy, minus the second component differentiated with respect to z. So that's f sub y differentiated with respect to z. So that's the first component of our curl. And you can see that these mixed second order partial derivatives, if f sub x, y, and z are continuous, they are equal. So what we get here is 0. And similarly for the other two components, if you plug those components in the definition of curl, you will get zeros. So this is going to give you 0 times I plus 0 times j plus 0 times k. So you get the 0 vector. Okay? So as a consequence of this theorem, what we have is, if you have a conservative vector field, so that's a corollary, a consequence of this theorem is that if our vector field is conservative, meaning that there is a function of which this is the gradient vector field. So if capital F is conservative, then its curl is going to be 0. Okay? So that's because F can be written as nabla little f, and the curl of such vector fields are 0 because of this theorem. All right? So let's look at another example now. Basically, looking at the previous vector field, the vector field from the previous example, show that this vector field is not conservative. Okay, so pause the video and input your explanation below. All right, so I hope you paused it and realized that this computation that we did before for the curl of f shows us that it is not a 0 vector, so it cannot be the gradient field of some function, because if it would be, then we would have to have the curl be identically 0, and it is clearly not identically 0. Okay, so that's the explanation of this this statement. And finally, let me tell you another theorem about another theorem, which tells us that if our vector field f is defined everywhere, so on R3, defined everywhere in R3, and its curl vanishes identically, meaning that it vanishes everywhere, it is 0, then it is a conservative vector field. So this is something we'll prove in a later video. Let me give you the last example. So consider the vector field f with components y squared z cubed plus 2xy z cubed plus 3x y squared z squared, and show or explain that this is indeed a conservative vector field, and also find a function of which this is the gradient field. Pause the video and input your explanation below. Okay, I hope you paused it and computed the curl of this vector field and found it to be identically 0. So you found that it is indeed 0 everywhere, the curl of this vector field. And it is also clear that this vector field is defined everywhere in R3. So this theorem applies, and it means that this vector field is conservative. So there is a function of which this is the gradient field, and it's easy to see that that function, f of x, y, and z, is just x times y squared times z cubed plus any constant. So if you take that product of x, y squared, and z cubed, differentiate with respect to x, y, and z, you will get these three components. Okay? I hope you enjoyed this video, and I'll see you in the next one.